Okay then, so today I want to talk about a very important idea in projective geometry called the idea of a harmonic set. So a harmonic set is a set of points on a line which has a special property. And to generate one, you can use a complete quadrangle. So to make a complete quadrangle, you just put 4 points down on the plane so that no three of them are collinear. And then you just draw all the 6 possible lines which link pairs of points. That'll give you your complete quadrangle. So we'll call these initial 4 points the vertices. And by drawing all these possible lines, we have this really important figure called a complete quadrangle. Now, in addition to these 4 vertices, these new lines have sort of created some extra points. In particular, there's one here, there's one here, and there's one here. So we call these 3 points diagonal points. I've discussed this before. And a harmonic set is formed by, if you draw a line which goes through any 2 of these diagonal points, okay, I better extend that line a little bit. Right, and then let's call this line G, okay? G is like an external feature, if you like. It's not really part of this complete quadrangle. It's an additional thing that we're superimposing. And we'll have a look at this line G. I better write G the proper way up. Now let's look at all the points where lines of our complete quadrangle cut through this line G. So there are 4 points here. And it turns out that these 4 points form what's called a quadrangular set. Okay? So, in particular, if we call this point A, and this point B, and this point C, and this point F, then we write H, A, B, C, F. Now, don't worry about it too much because I'm going to go through this terminology in a rigorous way soon. But I just wanted to motivate the lecture. So this notation in words would say that AB is harmonic conjugate to CF, or C and F are would say that C and F are harmonic conjugates with respect to AB. It's a little bit long-winded, but if you look at this diagram, you can see that like A and B have a kind of similarity in that they're both diagonal points, and C and F also have a kind of different similarity in that they're both formed by these individual lines. Sorry, that's there. What am I doing? Yeah, they're both formed by these individual lines which pass through this third diagonal point, which wasn't involved in our section G, our cross section. So this is just one way to form a harmonic set. Now, why should we care about harmonic sets? Well, one of the most important reasons is because these are invariant under projections. So, in particular, this is probably one of the most important results about these things. If we have 4 points on a line, and we have A, B, C, and F, and we have that these are projective, there's a projectivity from here to A dash, B dash, C dash, F dash, and we also have that A, B and CF have this harmonic property. So if all of that holds, then it implies that A dash, B dash, C dash, F dash also have this harmonic relationship. Now this is crucially important because you can do a heck of a lot with projections. I mean, we could, for example, we could set a point here, like we could set our eye here, and then we could do a projection, zoom, 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 and project these 4 points onto, so let's say, this line over here, and then we could project those over here. We could do loads of projections and things, but the resultant 4 points will still have this special relationship. So just to begin with, let me just define a figure as a set of points and lines. It's basically just a picture in 2 dimensions. And a section of a figure by a line is the set of points on the line which are intersected by lines of the figure. So it's basically just like a cross section. It's a one-dimensional cross section of a picture, essentially. So the key sort of object for us to look at today is a quadrangular set. That's what they call them, quadrangular sets. And a quadrangular set is just a section of a complete quadrangle. A complete quadrangle is where you have 4 points and you draw all the possible 6 lines between those points. So I'm talking about these 4 points here for this example, and I shall draw all the lines in between them. 1, 2, 3, 4, 5, 6. Okay, and so a quadrangular set with respect to a line, let's say G, let's say this dotted line here is called G. There it is. Okay, it's not exactly very, let's say, dashed, whatever. This is the line G. And this is a quadrangular set because if we mark all the places, I'll use circled points. These 6 points here on this line G form a quadrangular set because they are the 6 points where this line intersects with this figure, which is a complete quadrangle. So we like to work algebraically, and so it's nice to be able to convert this kind of idea into something which we can talk about algebraically. In order to do this, we need to label these different points. So we can label the 4 vertices from this complete quadrangle. Remember, a complete quadrangle is just where you put 4 points down and then link them with all possible lines. So we'll label the vertices P, Q, R and S. This is just following Coexeter's convention. And then we're going to name these points on G, on this quadrangular set. So we're going to label them, there's 6 of them, so we'll call them A, B, C, D, E and F. And the convention for labeling them is a little strange. I strongly encourage you to spend a little time to familiarize yourself with it. So basically we pick this final point S, and we then look at, in alphabetical order, all these lines that go through S, and those define A, B and C. So this is A equals PS, and then Q comes after P, so this is B, and B equals QS, well, dot G of course, because it's intersecting with G, and then C is R of S, dot G, and now the last 3 of these points, they're the opposites of A, B and C respectively. So any edge on this thing, let's say this one here, which is the edge that makes A essentially, this has an opposite edge in the quadrangular set, which is the edge which doesn't have any vertices in common with, this edge has an opposite edge in the complete quadrangle, which is the edge that has no vertices in common with it, this edge here. So that will be the edge that defines D. So this would be D. So D would equal QR dot G. And similarly, to find E, we look at B, which is this one here, and we get this one here, which is PR dot G. And F, C is RS. RS is here, opposite edge is here, so this would be F, which would be PQ dot S. So have we got them all? A, B, C, D, where's E? E is PR, which is here, okay? So there we have it. Okay, so I meant to put dot G here, just to recall, for example, PQ is the line that passes through points P and Q, and dot G means that we're talking about this line intersecting with this line. It's the point, the common point of these 2 lines. Okay, the common dot. So this is just a notational convention. The convention that we pick the last alphabetic letter of the quadrangular set S, we look at all the lines through them in alphabetical order to get A, B and C, and then we get D, E and F by looking at what happens to the opposite edges and how all those edges intersect our line G upon which our quadrangular set is generated. Now we denote this quadrangular set, A, B, C, D, E, F, we actually write it like this. The notation is quite telling. We write it like AD, BE, CF. That's what we shall call this quadrangular set down here. So notice just alphabetically we've coupled every letter with the letter that comes three letters away from it in the alphabet. And you can see the relevance of this just by looking at the diagram, because A and D are opposite sides of the quadrangle. Well, the edges corresponding to A and D are opposite sides of the quadrangle. You see they're kind of converging here. Similarly, B and E are these two edges here, which are again converging. And C and F are again opposite edges of a quadrangle. They happen to meet in the middle. And so the point here is that this notation kind of compactly and algebraically represents this quadrangular set. However, all of this was based on the way that we originally labelled the vertices of this quadrangle, the way we labelled this one Q, you know, etc. Q, R, S, P. But ultimately, it shouldn't matter what way we labelled these things. And so, basically, this notation is kind of equivalent to other notation. In other words, we can write a different ordering of these letters, and that would just correspond to labelling the original quadrangle in a different way. But we're interested in more robust properties than just how stuff's labelled. We're interested in a really kind of fundamental geometric properties which shouldn't really depend on which vertex we decide to call Q, P, Q, R, and S. So, in other words, this notation here is really equivalent to lots of other notations. So, for example, what we could do is we could swap around the order of these particular things. For example, this is really equivalent. Okay, I'm talking like this now, so I'll just box this off. It's equivalent to BE AD CF. Because if we wanted to make the second one, all we'd have to do would be to permute some of the letters on here, and we could get this kind of list instead. So, in other words, we're free to swap around the order in which these three pairs appear in this list. So this is also equivalent, of course, to AD CF BE, or just for completion, CF BE AD. All of these things basically represent the same thing, just as if we'd labelled the original vertices of our quadrangle in different ways. So I strongly encourage you to check this. See, obviously, we got this quadrangular set here, and then I've just told you that we're going to use this convention here of writing it like this. However, if we relabeled it, let's say we'd called this one Q, and this one P, and again this one R, and this one S. Well, if we'd labelled the original quadrangle like that, and then we'd applied these rules again, then we'd have ended up with this particular set here. So you should probably check that for yourself. Anyway, we're not doing that, so you can just ignore this. Okay then, so just to recall, these P, Q, R, and S, these are just the labels of the original vertices of the complete quadrangle, and they're kind of arbitrary. However, these are the rules by which we label the different elements of the quadrangular set. There are 6 elements in this quadrangular set. There's 6 points on this line, or there may be less if some of the lines intersect upon G, but anyway, usually will have 6 points on this line that constitutes the quadrangular set, and this is the notation for it. And you can see that there is some sense behind it. We basically write this as 3 pairs of points. A and D are paired together because they are generated by opposite edges of the quadrangle. Similarly, B and E, opposite edges of the quadrangle. Similarly, C and F, opposite edges of the quadrangle. In fact, they're the special ones which have a crossing point inside the quadrangle. Okay, but the point here is that although A, B, C, D, E and F are generated via these rules, the labels of P, Q, R and S are somewhat arbitrary. And so if we swapped around those labels, we should really still be talking about the same quadrangular set. So what that means is that we can do certain permutations of the letters in here and still really be talking about the same quadrangular set, just generated by a quadrangle which was labelled differently. So, for example, what we could do is we could swap around P and Q. So if we swap those two around and applied these rules, so I know this notation takes a bit of getting one's head around. I strongly recommend you to... so the point is that if we change the lettering of our original quadrangle, it shouldn't affect the essence of our description of a quadrangular set. So what that means is that this notation here for a quadrangular set is equivalent to some other notation which would correspond to us just swapping around the labels of P, Q, R and S. So, for example, suppose we swapped around the labels of P and Q. Well, in that case, if we apply these rules again, now I shall use bold writing. Think of this as representing different letters, like bold A is not necessarily equal to blue A, etc. And if we just apply these rules again, but under this different labelling where this is now P, this is now bold P, and this is now bold Q, and bold R and bold S are the same. Well, applying this permutation, swapping P and Q, we apply these rules again. We get, again, A is PS.G, which now is QS.G. So what was originally A is now B. What was originally B is now A. Similarly, what was originally D is now E. What was originally E is now F. Sorry, E and D swap round and A and B swap round. Okay, so now if we write down our quadrangular set in the standard way and we apply these substitutions, which come about because our letters have changed because of this permutation, we get that AD is now bold AD is equal to ordinary type BE, bold BE is equal to ordinary type AD, and CF is unchanged. So we see that this basically is equivalent to this. So what this is essentially saying is that this notation here is invariant if we swap round this first and second pair. So this essentially is equivalent to writing BE, AD, CF. And it can also be checked that it's also equivalent to writing AD, CF, BE. That's part of the magic of this notation. It doesn't matter which order you write these three pairs in. You're essentially describing the same object, perhaps just with a relabeling of the names of these vertices. This is one kind of permutation that we can do. Swapping around P and Q here. Essentially, basically what I'm saying is that this sort of notation is equivalent to these notations here, where we're essentially just swapping around the order of these three pairs. So we can permute the order of these three pairs, and it doesn't really affect the essence of the quadrangular set we're discussing. So essentially, these three pieces of notation are equivalent. Now, there's another kind of permutation we can also do, which also leaves things invariant. We can do this kind of permutation, where we take a couple of these elements, we take sort of two consecutive letters and swap them round. Best to just look at the actual effect of this. So the effect of it, essentially, I'll just show you the output. The effect of it here is shown here, and it is that we can essentially swap. We have three pairs in here. We have three pairs of letters. And what this is basically saying is that we can swap round the order of the letters in two of the pairs. We're free to do that, and that essentially doesn't change the set we're talking about. So instead of saying A, D, B, E, C, F, we can say A, D, E, B, F, C. So we've swapped round the entries in the last couple of pairs, and that essentially doesn't change the set we're talking about, up to permutations of the labels of the vertices of the quadrangular set. So to see this, just consider this permutation here, where we'll relabel what was P, we'll call it R, what was Q, we'll call it S, what was R, we'll call it P, what was S, we'll call it Q. So what effect does this have on our original lettering? Well, using this rule here, our standard rule, that we'll find A, B, and C by looking at the edges which go through S, through Q, P, and R, and then we'll find D, E, and F as the opposites of those edges. Well, using that kind of notation and this kind of permutation, we find that A used to be called PS, but now P's become R, and S has become Q. So that becomes QR, which is D. And so on and so forth. Maybe you should pause the video and check this for yourself. Actually, I encourage you to do so. And when you make those permutations, so you permute these letters in here, that causes the outputs to permute, which causes the sort of 6-letter code for the quadrangular set to change. And essentially the effect of it is that we've swapped around the order of the entries of the first pair and of the last pair, and left the middle one invariant. And this is, you can also sort of see this geometrically as well. If you think about this quadrangular set here, if you changed around the orders of these two, you should see that it wouldn't really affect the kind of figure that you get. So just to summarize about our quadrangular set notation, we'll keep this notation of coexitors about the definitions of A, B, C, D, E, and F. I'm not 100% fond of it, but you've got to call them something, and we'll get used to this as we carry on. But this is the real elegant part of the notation, because since we have things in three pairs, it naturally reminds us about what kinds of operations essentially leave the object unchanged. I mean, it's sort of similar to in set theory, that the set 1, 2 is equal to the set 2, 1. But we can write things in another way around and we're still talking about the same object. Well, in a similar way, we're allowed to permute the order in which these three pairs come, so these are all equivalent, and we're also allowed to permute the entries in a couple of pairs. Okay, so we can swap round the entries in this pair and the entries in this pair, I'll leave the third one invariant. Okay then, so let's get to the discussion of some results about quadrangular sets. So this is one of the most important ones. We're going to discuss it for quadrangular sets in general, but we're going to see that it has special applications for specific kinds of quadrangular sets, which are fairly important. And it's also very interesting to see Desague's theorem and its converse working here. Those important results we discussed in the previous lecture. So the basic idea to start with is that we have 5 points on a line, A, B, C, D, E. And the first thing we want to show is that given any 5 points on a line, there will be a quadrangular set which contains those 5 points. So basically we're going to show how to create a 6th point and complete the quadrangular set given generic 5 points on a line. So how do we do it? Well, we'll call our line little g and click. Basically we're going to start by drawing a triangle. Now I'm going to use the same kind of labeling convention as I was discussing before, although that's not necessary. All that matters is that you pick 3 points, 3 out of these 5 points, and you draw a line through each one. So I've drawn a line through C, B and D, and I've labelled the vertices Q, R, S. So basically I've used 3 of these points, drawn lines through them to form a triangle. The next step is to draw in a couple more lines. So in particular we draw a line through another one of these points that we haven't touched yet, A, and we'll draw that line through S, and we'll draw another line for a point we haven't touched yet, E. We'll draw that through R, and the place where those 2 lines intersect we'll call P, and that's the 4th vertex of our quadrangle. And then we just complete the quadrangle by drawing all the edges in, and we create an extra vertex which is just off the screen. It'll be visible in a second. There it is. So that's point F. So now we have 6 points, we have a quadrangular set. Now, what's the next stage? Okay then, so that proves that any 5 points can belong to a quadrangular set. The next thing we want to show is that not only do 5 points necessarily allow you to find a 6th point to complete the quadrangular set, but that 6th point is actually predetermined by the original 5 points. In other words, if you draw 5 dots on a line, then you've already fixed, subliminally fixed the position of that 6th point. It's already predetermined by the position of the first 5. So how do we show that? Well, we're going to do the same kind of construction method again, but this time we're going to use a different quadrangle. So we'll make this quadrangle in exactly the same kind of way. We'll call it P-Q-R-S-. And we do it by starting with a triangle Q-R-S, which is made by having lines go through points B, C and D, just like before. And we're allowed to do that because the labels of these vertices are somewhat arbitrary. And then once again we generate the 4th point of this complete quadrangle with the red lines by taking the meet of the line AS' and ER'. So there we have it, another quadrangle. So now what we want to do is to show that these two these two quadrangles, which were sort of created so that they generated the first 5 points, we want to show that they both make this same sixth point F. So how do we do that? Well, we're going to use Desague's theorem and its converse. So recall that Desague's theorem says, well, Desague's theorem plus its converse is basically saying that the vertices of two triangles will be perspective from a point if and only if the edges of those triangles are perspective from a line. And you can see the previous video if you want a reminder about that or how that result's proved. So it should be pretty clear that we have quite a few triangles that are perspective from this dashed line G, little g. Why? Well, because basically these quadrangles can be thought of as made out of triangles. So here's one triangle in, let's look at the upper green quadrangle for a start. So if we look at these points PRS, well, you can see that that forms a triangle, and that's going to be perspective. Sorry, we can see that this triangle PRS and P-R-S- are both going to be perspective from this line G. Why is that, and what does that mean? Well, what it means to say that two triangles are perspective from a line, it means to say that if we look at the corresponding edges, for example, SR would correspond to S-R', well, those corresponding edges are meeting at a unique point, the same point on this line G. So RS meets G at the same place as R'-S', RP meets G at the same place as R'-P', etc. So these two triangles are perspective with respect to this line G, and now Desague's theorem, or its converse, I'll just call it Desague's theorem, say it's an if and only if statement. I mean, last time I was discussing it as if it was two separate results, but really it's just, Desague's theorem just says that being perspective from a line is equivalent to being perspective from a point for triangles. And so Desague's theorem says that since these two triangles are perspective from a line, they should be perspective from a point. So there should exist some point, O, from which both of these triangles are perspective. So I've drawn it in there. You can see that this happens to be the case in our example. But what's nice here, I think the sort of clever part of this proof, is that we can carry on and look at more different triangles and basically apply this argument again. So if we look at the triangle QRS, well, that's going to, QRS and triangle Q'-R'-S', again, they're both going to be perspective with respect to G. And so again, they're going to be perspective with respect to a point. And if you think about the way that the edges work, they're going to be perspective, in fact, from the same point. So actually, if you like, what you can say here is that these are two quadrangles which are both perspective from this point O and both perspective from this line G. But that's just some extra terminology that you don't need to worry about for the proof, because we'll just carry on with what we've already discussed, and hopefully you should be able to see now that we can now find a third triangle which in both of these quadrangles which are perspective. This darker triangle here, PQR. So basically our argument so far implies that PQR and P'-Q'-R' are perspective from the point O. Okay, so what we've already shown infers that these are perspective from this point O, in the sense that if you draw a line QQ', that meets the line RR' and the line PP' at O. So this dark triangle that I've just drawn in
must be perspective from O, and now we can use Desague's theorem the normal way round, because we have two triangles perspective from a point, PQR and P-Q-R', which implies that they must be perspective from a line. And a bit of thought should convince you that that line is indeed G, this dashed line. So that infers these two triangles of perspective from this line, and that infers that QP must meet Q-R' on this line. And where does QP meet this line G? Well, it meets it at F. So that means that Q-R' must also meet G at F. So basically now we've shown that this point F, this sixth point of our quadrangular set, is uniquely determined by just specifying the positions of those first 5 points, which I think is really quite not particularly obvious, and it's very interesting to see how many different ways Desague's theorem works backwards and forwards to establish this result.
Okay, so what we have here is a complete quadrangle. We have 4 vertices, P, Q, R and S, and 6 edges, and I've circled these 3 diagonal points. Now, I've already talked about quadrangular sets, which are fairly general objects. So basically, to get a quadrangular set, we just pick pretty much any line we like and just rule across it, and then we can see which edges it crosses. The line we choose shouldn't go for any vertices, as in it shouldn't go through P, Q, R and S, but apart from that we have a lot of freedom. But hopefully you can see that there's actually a very special line that we could pick. In particular, if we pick a line that goes through two diagonal points, then that's going to give us a quadrangular set which doesn't have 6 points, it actually has 4. So what I'm saying is that if we choose our line so that it passes through these 2 diagonal points, that should do the trick. But if we pick G to go through 2 diagonal points, our quadrangular set is very special because it's only going to have 1, 2, 3, 4 points on it. And in that case, the resulting set of points on this line G is called a harmonic set. Okay, so just to, well, let's write it down here. This is a very important concept. It's probably, in a way, more important than quadrangular sets. So a harmonic set on a line G is a quadrangular set on G which passes through 2 diagonal points. Of the quadrangle. The complete quadrangle, that is. Okay, so this is an important idea. And if you have a look at this diagram here, this is our original picture for the quadrangular set. So it has it has 1, 2, 3, 4, 5, 6 points. That's a sort of general quadrangular set. Well, if instead of taking a section here, we shifted this section down a bit so that it passed through the place where these 2 lines intersect and these 2 lines intersect, then instead of having a generic quadrangular set would have a harmonic set. So, in other words, a harmonic set is basically, it's a quadrangular set where we have A is equal to D and B is equal to E. Remember that for an ordinary quadrangular set, we'd write it with the notation AD, BE, CF. But if we also have that A is equal to D and B is equal to E, then we'd have this kind of situation here, and we'd have a harmonic set. And we have shorthand for this because it's a very important idea. So to denote that these 4 points constitute a harmonic set, we write H A B C F. So that's shorthand. I use this notation to mean if and only if, and this is just shorthand for saying that the points A, B, C and F form a harmonic set, and because of the things I was saying about permutations of quadrangular sets being equivalent before, we know already that this is in fact equivalent to writing H B A C F, and it's also equivalent to writing H A B F C, and just for completion H B A F C, obviously. And it turns out, although I'm not going to discuss it now, but it turns out that when this relationship's true, this implies that H C F A B, but that's something we'll be discussing later. And we also have a more kind of wordy way to say this. So an equivalent way to express this information here or here is to say that, I'll do another big if and only if sign. These double arrows mean if and only if, okay? So we can say that F is the harmonic conjugate excuse my slanty writing, let's box it off, of C with respect to A and B. Okay? So we say that F and C are harmonic conjugates. Now, there's a couple of other things, sort of corollaries of our things that we proved for the more general harmonic sets. Anyway, let me, just to hammer it home, let me just label this. So that would be A, that would be B, that would be C, and that would be F. So you can see that C and F are basically these edges which go through a diagonal point which the line doesn't cross, whereas A and B are actually diagonal points. Okay. Now then, a couple of important results which we've pretty much already proved. One of them is that F, so okay, this is when we have this harmonic relationship, A, B, C, F, as shown above. So F is actually uniquely determined by A, B and C. That just follows from our uniqueness of the last point of the quadrangular set theorem, which we proved before. Now, another important result, which I shall leave to you to prove it, although I might discuss the proof in a later lecture. I'll call it the distinct harmonic conjugates theorem. Excuse my handwriting, I've set this up at a rather bad angle. I'll improve it in the future. Anyway, the harmonic conjugates theorem says this. It says that if A, B, C and C are all unique, so A does not equal B, B does not equal C, C does not equal A, whoops, that's an A, okay, and also we have that this harmonic relationship holds. So if we have those two conditions, then that implies that F does not equal C. So in other words, if A and B are unique and not equal to C, then the harmonic conjugates C and F are unique as well. And this is a result with very deep implications. So far we've been talking about harmonic sets of points on a line, but in an exactly dual way you could also have a harmonic set of lines which pass through a point. So that would be a set of 4 lines which happen to pass through a point, and it turns out that if you take a section of 4 such lines, as long as it doesn't go through the place where they all meet, that section will give you a harmonic set of points on the line that you take a section of it through. So if you imagine these 4 points meeting at a kind of star, and they're harmonic in the way that they do so, if you slice those with a section of an extra line and look where those star lines cross the extra line, G, then that will form a harmonic set, and the dual of that result also holds. So this is what we're going to get at next. So to do it, we're going to look at harmonic sets of lines. So we're going to look at the analogue of the problem we were just looking at, where we had, well, we were looking at it in a more quadrangular sense, but we also effectively tackled the problem point-wise of, given 3 points that belong to a harmonic set, how do you construct a fourth? And we found out that the fourth point, F in our case, we had A, B, C and F, we found out that F was uniquely determined by the positions of A, B and C when they were points on a line. Now we're looking at the dual case. So we have 3 lines, little a, little b, little c, and they're all concurrent and they all meet at this point. I shall just call that the star point, just verbally while I'm talking. Don't really have to refer to it too much. So they all meet at this star point, and what we want to do is we want to find a 4th line, little f, so that we end up with a harmonic set of lines. So in fact, the construction is really quite analogous to before. I mean, it looks a bit different, but if you follow it algebraically, it's basically the same. So what we're going to do is, given A, B and C, we're going to construct a triangle QRS. So that's with 3 extra edges, little q, little r and little s. So we have some freedom in doing this, but we basically have to draw these 3 lines Q, R and S so that where Q and R meet, A also meets, and where Q and S meets, B also meets, and where R and S meets, C also meets, as you can see in the picture. So we draw these red lines on. So now, if we define P to be the line which joins the place where A and S meet and the place where B and R meet, then we can finish the job by defining our last line F to be the place, to be the line between where A and B meet and where P and Q meet. And you can see that that meets with the other 3 initial purple lines, A, B and C, in the same place. So we have this kind of, we have these 4 lines all meeting concurrently. Now, if you recall, for definitions of a complete quadrilateral, the diagonal lines, a diagonal line of a complete quadrilateral is a line which has 3 points on it. And you should be able to see that A and B are both diagonal lines, and C and F, they're not diagonal lines, but they both pass through vertices which, if you joined them, they would form that final diagonal line. It's a good idea to go through this example alongside the example with the quadrilateral, and you'll see how algebraically it's basically a dual process which is going on here. Okay, so here's the punchline then. This picture should look relatively familiar to you because it's actually the same, well, pretty much the same thing as we were looking at before with the quadrangular sets. And it turns out that we can introduce the points A, C, B and F along the bottom line, Q, as we did before, although before we called that line G, but now we'll call it little q. It's that red line, and we introduce A, C, B and F, and also we'll define P, Q, R and S so that A, C, B and F relate to P. Okay, so points A, B, C and F relate to points P, Q, R and S, just as they do usually under the coexeter convention and as they did in the previous diagrams. And when we do that, we see that the line little p is the line linking points big P and big Q. The line little q is the line linking points big A and big B, and so on and so forth. You can see I've written how the lines relate to the points here. And the main point here is that we have the harmonic set of points A, B, C, F is in fact just the section of our harmonic set of lines, little a, little b, little c, little f. And so this is a very important result, because it basically says that if you take a section of harmonic lines, you get a set of harmonic points. So a more concise sort of projective way to say this is to say that if you have a harmonic set of lines that are projected out from a point which is outside of some other given line, L, let's say, actually no, yeah, L, I'll call it L, then if you take a section of those, well, if you look at how those lines project onto that line L, in other words, how L sections off those lines, that's going to induce a harmonic set of points on this line L. So projecting out, we find that the harmonic lines project to harmonic points. Another way to say it is that if you have a subset of a pencil of a point, and that turns out to be a harmonic set of lines, and you see where the members of that subset hit another given line, then the places where they hit that line, the members of the range of that line where these members hit it, will form a harmonic set of points on that line. So this argument and its dual together imply our harmonic invariance theorem, the thing I discussed at the beginning, which is basically that harmonic sets are preserved by projectivities. Why? Well, essentially we've just shown that an elementary correspondence, which is essentially where some rays coming out of a point match up with some points on a line, we've shown that elementary correspondences preserve harmonic sets, be they harmonic sets of points or lines. So, and a projectivity is just a concatenation, a combination of lots of elementary correspondences, from points to lines, from lines to points, etc. And every one of those will preserve the harmonic sets. So projectivities always preserve harmonic sets. That's a very important result, which we've just shown. And also, as a kind of corollary, I've got to learn how to say that word. Okay, so as a corollary from this, we also have, as I hinted at before, that if AB is harmonic conjugates to CD, then it implies that CD are harmonic conjugates to AB. Now, we can see this because previously when we were discussing, in the lecture where we were defining and discussing projectivities, we showed that if you have 4 points on a line, A, B, C, D, then you can find a projectivity to send those to points F, C, B, A, respectively. You can jumble up the order of the points. And so basically, since there is such a projectivity, and since harmonic relationships are preserved by projectivity, as we've just proved, it turns out that the harmony of AB being harmonic conjugate to CD implies the opposite, that CD is harmonic conjugate to A and B. So, or actually technically, I suppose we should say that C is a harmonic conjugate to D with respect to A and B. It's quite a mouthful. And remember now, since we can exploit the duality, these results are holding for harmonic sets of points on a line and harmonic sets of lines through a point.